Hello everyone, welcome back. This is chapter 6. We are going to focus more on chemical composition and specifically calculations related to chemical composition. So in the previous videos, you've been learning about how to write balanced chemical formulas. You learned how to name those balanced chemical formulas based if they were ionic, molecular, or acids. And then at the very end of chapter 5, you learned how to use a balanced chemical formula along with the periodic table and your knowledge of atomic masses to say how much one molecule of that substance weighs. So in this chapter, we're going to delve more deeply into being able to use a chemical formula along with a new unit to say something about composition of that molecule with regard to individual species. So as important as a chemical formula is, you need it to determine the mass of the overall molecule. It's not intuitive, it's not clear that you can make a relationship between the masses of the individual components to the total. So for what I mean by that is looking at NaCl. Now you can use that chemical formula to easily say, oh, in sodium chloride, I know that there's for every one sodium ion, there is one chloride ion. I got that from the chemical formula, the balanced chemical formula. But I cannot say that for every 1 gram or for every 1 AMU of sodium, there's 1 gram or 1 AMU of chlorine. Why can't I do that? I can't do that because the masses of sodium and chlorine are different, as is shown here and as you see on the periodic table. So, as important as chemical formulas are, we cannot use those chemical formulas directly to say anything about the relationship between the masses of the individual components. So because of that, we need to introduce a new unit when talking about amounts of chemical species. So these next 2 slides, I'm going to let you read on your own. They are just sort of background to kind of introduce the way of being able to count species based upon a mass, using this example of nails. What I want to get to, and so I'll let you read those 2 slides on your own. What I want to get to is this new unit that chemists use when talking about things that we count in chemistry. And this new unit, it's a quantitative relationship. And it's similar to like when we say a pair of something. A pair means 2. A dozen means 12, although I guess a baker's dozen is 13, right? I don't know if they still give a baker's dozen of donuts. A ream of something is 500. These are all quantitative relationships that we use in general when counting things. Well, when chemists count things, we like to count things like atoms, molecules, and ions. So what do we use when counting those things? We use this new unit that hopefully you will know and love by the end of this course, and that is called the mole. And just like pair, dozen, and ream, those have a quantitative relationship that is always constant, meaning a pair is always 2, a dozen is always 12. 1 mole of whatever you are counting, in this case atoms, is this huge number of atoms. So in scientific notation, which is going to be your friend when writing this number, in scientific notation, that number is 6.02 times 10 to the 23rd. So the take-home message from this slide is this new unit called a mole. And 1 mole of anything that you can count, be it molecules or ions or atoms or even donuts, 1 mole of whatever you're counting is this number 6.02 times 10 to the 23rd. And it's called Avogadro's number based from the Italian scientist that derived it. So you can think about this new number. It's just a number of things. So 1 mole of lead atoms would be 6.02 times 10 to the 23rd lead atoms. 1 mole of donuts would be a heck of a lot of donuts. It would be 6.02 times 10 to the 23rd donuts. So a mole, it's just a number of things. It's a way that chemists can do counting of atoms, molecules, ions, things that are important to chemists. So you may look at that number, or at least I hope you look at that number and say, oh, that's a huge number. It's an insanely large number, and you're absolutely right. It is a large number. You would think, why would chemists use or make use of such a large number? I like these two examples just to show you exactly how large it is. I like the second one in particular. If we really did all have $3 million a second for 100 years, none of us would need to take this class, I guess. But it is a huge number, and it's an insanely large number. But it is a number, the 6.02 times 10 to the 23rd, that makes sense to chemists, and it's a perfectly normal number when we're talking about things that are small, like atoms, molecules, and ions. Why is that the case? That's because 1 mole of those things that chemists like to count, 6.02 times 10 to the 23rd, that number generally makes up size objects that are of reasonable size, or things that we can actually see, touch, deal with on a regular basis. For example, let's say I was to dig in the bottom of my purse and I was to find 22 pennies, and let's assume that all of these pennies are 100% copper. All of the copper in those 22 pennies would equal 1 mole of copper atoms, specifically 6.02 times 10 to the 23rd copper atoms. If I was to get some helium balloons for a party, the amount of helium atoms in both of those balloons would equal 6.02 times 10 to the 23rd. So 2 large helium balloons contain approximately 1 mole of helium atoms. So it's a huge number, 6.02 times 10 to the 23rd, but it's a reasonable number for chemists to use because that number makes up objects of reasonable size, things that we can easily work with, manipulate in the lab. So this is the last slide for our introduction to the mole. You should know that the mole, it is the standard international, the SI unit for an amount. Now we're going to talk about in the subsequent video how we can relate moles to something that we can weigh. But for right now, you should know that SI, or that the unit for amount is the SI unit of the mole. It's abbreviated MOL, and that 1 mole of anything is equal to 6.02 times 10 to the 23rd of whatever you're counting, be it atoms of carbon-12 or lead atoms or shoes. So that is one definition of a mole that you're going to be using quite frequently in this chapter and in this course. In the next vignette, we're going to use this quantitative relationship of a mole to do unit conversion problems to convert between atoms of one species and moles of the same species.